Welcome to episode 41 of the What's Up podcast, recorded by Auld Reekie Astro. It's 23rd of January 2020. My name is Martin.
I'm Ali.
And I'm William.
Today we're going to cover a few news stories that have caught our eye over the last, we normally say few weeks, but in this case, the last couple of months.
Yes.
And talk about them and put a bit more science behind the headlines. But as I've alluded to already, I think the first thing we need to do is do a little bit of an apology because we've missed a couple of months of uploads. So we are sorry for that.
Is this where we dump excuses on the table?
I think we should, yeah.
What's my excuse? This is a new decade, so you're supposed to go into it going, yeah, full of energy. But the last decade kicked my butt, so I was tired and I slept a lot, and I'm changing jobs. So there's an excuse. So beat that with a stick.
I've had a lot of stuff on work-wise, and just very tired and dealing with a lot of stuff that needed my attention. And this has so sadly fallen by the wayside. And then Christmas and everything else. Top of that, William.
Have a baby.
Yeah, probably wins.
Yeah, he probably wins.
Yeah.
Do you know what we need? I feel like we need some kind of a
sleep.
road trip / wellness holiday.
I feel like this is sounding a little bit group therapy-ish.
Is it time for the Auld Reekie spa trip? I want a mud bath. I have some hot springs, please.
Nobody wants those pictures on Twitter. How is being a father then, William?
It is good. She's yet to grasp fundamental sort of principles of astronomy, but I'm trying my best. She has a book
straight out of the gate.
She has a book about astrophysics and lots of things with constellations on, but she doesn't seem to be particularly taking it in yet. But anyway, I'll keep pestering her to see if she can become an astronomer.
It's quite exciting. You had to move house during this as well, didn't you? So
there was a little bit of that as well. Yeah.
And I'm in the same house. My excuse sucked. Maybe all three of us could just blame you and your wee one for us not talking astronomy for the last few months.
Let's take this back away from our personal problems and more towards the astronomy. We were going to talk about something that's gone boom, a thing that might go boom, and a thing that could make us go boom. So let's start off with the thing that might go boom.
It may go boom. So this is
it will go boom.
It will eventually.
Yeah.
So I'm glad we're talking about this. So the delay has actually helped because the story's been sort of getting fleshed out over the last several weeks. Over the Christmas period, one of the brightest stars in the sky, one of the most famous ones, I think, because it's nice and colourful, has dimmed quite a lot by like a factor of between 2 and 3. Which is enough that your own eye can see it. It was in the top 10 brightest stars in the sky. It is now not even making the top 20. And
Noted.
It's a variable star, so it does wobble, but it's very, very rare that it wobbles as much as it has done. So lots of people got excited. And on Twitter, there was lots of the astronomers that I follow were all sort of going, it's almost certainly not a sign that it's about to explode as a supernova. But it still didn't stop people from speculating and having fun. So backing up, the star in question is Betelgeuse. I'm probably pronouncing that wrong, but as far as I'm concerned, thanks to the film, it's Beetlejuice. Beetlejuice. I've said it 3 times. It's a lovely red star in the top left-hand corner of Orion. So it's Orion's top left shoulder. And it's a fun star for a few reasons. Right. So it's the top left corner.
It's right. It's his right.
This is looking away from us.
Oh. It's one of the shoulder stars.
Don't make me do mental flips. It's one of the red ones in Orion. And it's a fun star for lots of reasons. So yes, it's bright, but it's also the very first star outside of our own sun that we were able to actually resolve spatial details of. So that's kind of cool.
I mean, take a picture that you can actually see what the surface looks like.
Yeah. So I spend a lot of time explaining to people that most stars are so far away and so small that even with the Hubble Space Telescope, it's much smaller than a single pixel. So you're never going to see anything except just a dot of light. And then you do all your science with that dot of light. Whereas with a star like Betelgeuse, if you work really, really hard, and I think Hubble was the first telescope that was actually capable of doing this in one direct image go. The people that had done it before had to combine telescopes, and it was interferometry doing it. I think that's true.
I don't think Hubble's done it.
I don't think so. Hubble's not the resolution to do it.
Hubble's not the best resolution.
According to the wiki page, Hubble was able to get in and do it. I bet it was drizzling. Because it's not far away from 50 milliarc seconds.
Hubble's not that great.
Not drizzling.
They call it drizzling. It's like the drizzle pack software that they get. Actually, they add 4 different pointings together, and you can get subsampling.
I think the first image was done with the VLTI.
We're going to edit this, aren't we?
No, I like this.
I thought it was VLTI, but okay. Yeah, if you're going to sum to sub-pixel, then okay, I'll give you could do it with the Hubble. But
I'm only going with Wikipedia's first paragraph.
No, optically, I don't think you could do it because the VLTI is like it's 50 times the diameter of Hubble. and they're only getting like 3 or 4 pixels across the surface. No, more than that, like 10 pixels across the surface.
We can
double
do this
check
fast later.
We can double check. I might be wrong, and so I thought it was a little bit beyond what Hubble can do as well. So I guess I should put this in context. So we're talking in terms of arc seconds. So if you hold your pinky up at arm's length onto the sky, that's about 1 degree across, and you can subdivide a degree into 3,600 arc seconds. And an arc second is a good number to have in your head because that's roughly how good you can do because of the Earth's atmosphere if you're looking in the optical from the ground. We can do better than that if you have very expensive telescopes that can correct for the Earth wobbling, or you can go into space and then your telescope, depending on how big your telescope is, that is your limiting resolution. So Hubble can get down to 5/100ths of an arc second, which is pretty darn impressive. And ALMA can do even better. So we're talking milli-arc seconds, so 1,000th of one of those 3,600 slices of a degree. So tiny slice of sky, but it's enough that you can see Betelgeuse is weird looking. So it's not perfectly spherical. It has a little hot spot on one side. And the star itself is massive. So one of the reasons we can even remotely get close to seeing details on the surface is because it's nearly the size of Jupiter, which is also kind of cool. So if you were to replace our sun with Betelgeuse right now, it would extend out to at least the asteroid belt, if not a bit further. There's some uncertainty just in getting those exact numbers. And so it's impressive. It's officially classed as a supergiant star. It's got a cold surface, or coldish, which is why you get that lovely red color. It's not bright hot like white like our sun.
So it's cold by comparison to the sun.
Yes, still a nice toasty, 4,000 degrees Kelvin or something, but it's cool in terms of stellar photospheres. And the reason it looks so interesting right now is because it's finished burning hydrogen in the core, and that means it's no longer a main sequence star. It burnt through its hydrogen really fast because it's quite a high mass star. So it's only about 10 million years old. So the dinosaurs wouldn't have had Betelgeuse in Orion, for example, which is kind of cool thinking about it like that. And within the next 100,000 years, that seems to be the current estimate, it is going to explode as a supernova. That's what we know about those massive stars. It's currently burning a bit of hydrogen in shells instead of in the core, because this sort of interior contracts and heats up and allows fusion to carry on, but not in the core anymore. And then the core can heat up even more and start fusing helium, and the outer layers get caused to puff up, which is why you get this supergiant phase. And to be honest, the supergiant's a little bit of an arbitrary definition as well, because it's more to do with luminosity than it is to do with physical sizes, for the same reason that we can't measure these sizes easily. So that was a lot of chat for one star.
It's a cool star, though.
But because it's big and because it's got this hot spot on it, we know that there are sort of regular pulsations and variability. So it's not very stable. And you get a lot of stars that are like this. Cepheids variables, they're much more regular. They have a very periodic, they get brighter and they get dimmer. And that's because the star itself, we like talking about stars being a perfect balance between gravity trying to crush the star and the energy from the fusion holding the star up. So that energy stops it from collapsing any further, and you get this perfect equilibrium, and the star just shines for billions of years. With these evolved stars, they're not perfectly stable. So the atmosphere can condense a little bit too much. It gets a little bit opaque, and then that causes it to get fluffy and get puffed out too far, and then everything cools down, and then it collapses. So it's this sort of pulsating cycle. So you have a bit of that going on. And there's other weird stuff happening to do with convection. So you actually get in really massive stars like this, the theoretical models in the computers, they tell us that there should be huge amounts of stellar atmosphere sort of rising. The hot stuff rises like a lava lamp and comes to the surface and then falls back down. But these are huge regions on the star that is Betelgeuse. Our sun has them, but they're a lot smaller, and you can actually see tiny granulations if you get the high resolution images of the solar surface. So that's the same thing: hot regions rising, small regions, cold regions descending. But in Betelgeuse, this is a much bigger process. And it dredges up all kind of weird stuff from below in the star's interior. And these things can sort of align, and occasionally you'll get a double dip, if you like, so everything gets much dimmer than usual. So it seems like we're in one of those periods right now. But it's still the dimmest it's been for quite a long time. And that's exciting for people that have been staring at this. And this has been stared at since antiquity. There was a paper saying Aboriginal Australians were well aware that Betelgeuse was a variable star, and we've known this for a very long time.
Variable, not just that it was...
Yeah, so not just Betelgeuse, I think Aldebaran was one as well, and Antares. I think the three of them all show very long period variations if you've got nothing else to do with your time, but pay attention to a beautiful non-light polluted night sky. You can pay attention to some of these things changing just ever so slightly, but just enough to see. And this is why it's fun. Have you been out to see Beetlejuice looking dimmer? Because it does look dimmer. It's noticeable.
No, I've not.
It's comparable in brightness to the top right-hand star in Orion. So is it Bellatrix? Is that?
I think it's Bellatrix, yeah.
So it's similar in brightness to Bellatrix at the moment, or at least it was the last time I got a clear sky to actually go and look at the bloody thing. But yeah, it is a noticeable drop, and it will probably come back up to where it was. So it's going to be back in the top 10 in the not too distant future. But it's kind of fun. And because it's got any time between now and the next 100,000 years to go supernova, the odds are not good that we are lucky enough to see this thing go. And I thought it was quite interesting. If it is going to explode as a supernova, it's going to be spectacular. So that's why I think even supernova experts still want it to go supernova in our lifetimes. And it's also interesting to bear in mind how far away it is. It's more than 600 light years away. So if it was going to go supernova in our lifetimes, it already has done, and the light just hasn't got to us yet. Or it hasn't, and it's going to be chipping away for 50,000 years before it does anything interesting.
So I think when it does go supernova, there's a good chance it'll be visible during the day.
Yeah.
I
think brighter than Venus and comparable to the full moon in the best case scenario, I think. But that's, I don't know. You maybe have to be awfully optimistic for the numbers to make that happen. But, it look amazing.
Really exciting. Pretty sure that every single telescope on the planet would be pointing for a little while.
Yeah, well, we're so close that all that expanding, we already know there's like shells of dust that are getting thrown off this. And this is really important in terms of us being here. The interstellar medium needs things that aren't hydrogen and helium to build humans and planets with, and jewelry and whatever else you care to have on your planet. And one of the ways that you can enrich the interstellar medium is these massive stars. They lose a huge amount of their own material through wind. So our sun does this, but on quite a small scale, and big puffy stars like Betelgeuse, they can't really hang on to the stuff that's really far away from the interior. So the energy just drives these massive winds, and it just flows out. You can see the dust in some of these ALMA images. I think ALMA's got the best resolution snapshot of Betelgeuse so far. But
I think I've seen things saying that depending on the wavelength you use to look at it, it's different sizes, effectively, because
you're looking at different stuff.
Yeah, you see through different materials. So the diameter of the star depends on the wavelength you're looking at, which is kind of quite a weird way to think about it. I mean, that's obviously not quite true, but I think thinking of it like our sun as a nice sphere with a sort of surface-ish, it's a bit more blurry. I mean, quite literally a bit more blurry. It's quite cool.
The ALMA paper's got a nice image where they draw a circle on it, and I think they call that the photosphere. Right. So I'm not sure if they're getting their measurement from the ALMA results, or if they know that's from previous. I think it's an infrared telescope that's done it, and that's the best estimate of the photosphere. So ALMA's like, okay, that's there, and then here's what ALMA can see on top of that. But it's still really cool, and it seems to be the polar regions are where the hotspot is. So that hotspot's been seen before. And the star's sort of rotating almost edge on to us. So one side is slightly bluer and one side is slightly redder.
Nice.
If you've got really high resolution data, you can see that rotation. Or you can see it in the data, sorry. It's not like we have a glorious movie of Betelgeuse rotating, but maybe someday. But the hotspot is, they think there's one of these convection cells. It's a bit roguelike, and it's just bubbled up, and it's throwing out a lot of extra material in that direction, but you get this extra hotspot too. So lots of interesting stuff. I mean, it's one of those things where you just take it for granted. It's like, Betelgeuse is just there. It's like one of the first stars you learn about. And then the more I start digging, the more I'm like, I don't know enough about stellar evolution or Betelgeuse to fully understand this, but I'm impressed that so many amateur astronomers have been paying attention to this. They have a very active, the AAVSO, is it Amateur Association American Variable Star Observers, something? I've got the acronym wrong. But they have a website. So if you're really keen to go and do this, they'll give you advice. You can go and by eye try and very precisely estimate magnitudes of stars on the sky. You can do it with your CCDs if you really want to take pictures. You can upload your data, your light curves, your spectra. They're actually uploading spectra of this thing. So I'm kind of impressed that there's a huge amount of people paying attention to this when I frankly wasn't. But it's interesting. It's so bright. It's not something we monitor as standard. In surveys, it's overwhelmingly bright. So most of our survey data would be like, oof, that's masked Betelgeuse out because it's washing out everything. It's interesting.
So moving on from a thing that might go exploding in our lifetime, but probably won't, something that definitely has exploded in our lifetime, because it happened last week.
Yay!
This was the test of the Falcon, well, particularly the Dragon capsule. This is again SpaceX, the Dragon capsule, which is their intended to be crewed capsule. The escape system. Should a rocket fail and go wrong, how do you get your squishy humans away from your exploding rocket nice and safely? And the answer is naturally with more rockets. So this was testing if you launched. This is a real. This did this for real.
This just sounds like something out of Kerbal Space Program. More rockets.
That really doesn't work in Kerbal Space Program for me. So they launched a Falcon 9 with a Dragon capsule on top, and when they reached a certain altitude during the launch sequence, they decided to simulate something going wrong on the Falcon 9. And almost like a champagne cork, the Dragon capsule uses Draco engines, which are on the bottom of it, to separate itself from the rocket, get a bit of distance between them, and then come back down safely to Earth, while the Falcon 9 went pop behind them and did blow up.
They went to 11 with it, didn't they? It was like, because they could just pretend and leave the rocket firing normally and just test the thing, but they decided to explode it too. Is that partly to see if any debris makes it up to damage the spacecraft?
So when you may as well test it properly. It was a veteran Falcon 9, they said, so it's only been used a number of times already. So it wasn't like it was a fresh new one. It was a well used one.
I wonder what the stats are on. Did they have like a dummy in the seat with accelerometers to try and measure?
Yeah, like, what are the G-forces?
I assume they've instrumented it, but I don't think they've released those figures, because it is interesting. Because obviously this was on the best analog I could think of was the Saturn V. Saturn V had basically the same thing.
Yep.
When you launched, but what was different is I saw a great image of a Saturn V escape mechanism, which is of course you've got the capsule, and then you've got this sort of long prong sticking out the front of it, which is the escape mechanism, which has lots of rockets on it. So when they fired them, you just see like the capsule sheathed in flame as all these rockets that are mounted above the capsule fire.
And you're basically firing through your own rocket exhausts to try and leave.
But you don't care because you're alive.
I mean, it works, yeah. And it was. I don't think it was ever used, but
I think they used it when there was a fire on the pad for one of the earlier ones, but it was uncrewed at the time. Yeah. But it did look spectacular. There's a video of it. It's a bit grainy, but
so the Draco engines are thankfully mounted underneath the capsule in this case, so it does just look a little bit less horrifying. And then I say they launched the capsule away cleanly. They got a bit distance behind it, and then they jettisoned the back of the Dragon capsule, and the capsule itself floated merrily back to Earth using parachutes, landed in the water, and was scooped up by a rescue boat.
So a successful test.
Very successful test.
It's kind of hard to bear in mind because you've got to. This is the first stage of the rocket is pressing into your back already. So you're pulling however many Gs. Is it 2 Gs or something by that point? Maybe I know Saturn V got up to about 4 Gs before the first stage was empty. So there was almost no fuel in the bottom stage, but you had these 5 massive engines. So you're properly crushed into your seat. So for your escape motor to work, it has to do better than 4 Gs. Yeah. And that, we're talking spine-shattering type changes there when they kick in.
This is a very short-lived, very unpleasant experience, but it's that or you go kablamo.
True. I would definitely take dodgy spinal damage over kablamo any day, I think.
And, I mean, fighter pilots do 6 Gs? During a high
I was thinking it's more the sort of the acceleration of the acceleration. Does that make sense? Because, if you turn it up slow, you could potentially get your body adjusting to it, and that's kind of what rockets do. But that moment when you turn on that first motor that's crazy powerful, that's got to be horrible.
Yeah.
It's equivalent of a car crash.
There was something, I think the highest G experience was a Soyuz capsule, I'm sure, where there'd been an aborted launch. I can't quite remember what it was, but
probably something similar. They've used an escape mechanism because they are, and it was horrible,
insane. Yeah, it's like tens of Gs, and the people should have been jelly, but they survived.
There has been a higher one.
Somebody got up to 100 G.
Yeah, what? There was a rocket sled accident. I forget the full story behind it, but they were doing rocket sled tests in this 1940s, 50s probably. Yeah,
it was the same person holds a lot of the records.
And they put too much fuel in, or they launched it too quickly, and the guy experienced far too many Gs.
But survived. Amazing, isn't it? I suppose if it's very brief.
Oh yeah,
you can.
Yeah, if it's a tiny fraction of a second, like a millisecond of 100 Gs, you could potentially be fine because there's not enough time for that to set up all your brain sloshing around inside your head. And it's to do, like, you have to worry about eyeballs out versus eyeballs in and stuff, like which direction are you putting the Gs in? So your spine is obviously a bit fragile, but if it's into the square of your back, it's not so bad.
Fine.
Well, I think the Dragon caps, you're lying on your back. So it is
it's eyeballs, way to do eyeballs it. In. Yeah.
That raises another question there. You're saying about it was an old Falcon 9 launch. When they do launches with people, which is coming fairly soon.
Very soon.
Do they use a brand new Falcon 9, or do they use one which has already done 1 or 2 trips, so it's sort of almost been tested?
It's a good question. I suspect they'll use fresh ones because that'll be the safest option.
Then you almost feel like you've got more trust in one which has done a couple of launches and survived.
It's a good question, and one that will be tested fairly soon because they're talking about doing crewed test flights. They were talking about doing the end of February. It now could be early March.
Right, but it's not.
But it's not long. This was kind of almost like the last hurdle to cross to show that it was safe for human test flight.
So do they do that to the space station, or is that the first one's just purely...
That'll be quickly
up and
pop
down.
up and back down again.
Yeah.
Didn't Starliner have a recent hiccup as well? Because they were meant to resupply and there was something wrong with the clock on their one. So it ended up not making the orbit it was supposed to, which was a little bit depressing. Because
on the Ryan,
both Starliner and Dragon have had their own delays. Mm-hmm. So we're still a bit away from getting humans up from somewhere that's not Russia.
But it's pretty...
Or China.
These are all moving very quickly. So. And there'll be lots more options in the near future for your space holidays.
Yeah, I'm curious to see what China's one looks like as well. That's going to be kind of fun because they're still talking about sending taikonauts to the moon. It's going to be fun.
Yeah,
can't wait. I'm
sure they'll be first. But yeah,
this decade, maybe, maybe.
Yeah, possibility.
Yeah,
for the Chinese, not Americans.
I think America could do it if they would.
Well, yeah, they'd have to fund it slightly more.
Yeah, sort of a longer term funding commitment.
When did shuttle stop? 2011.
Mm-hmm.
And
plus, there's
nearly been it's getting once a decade.
Plus, I think it's hard to justify an Apollo level expensive program while your climate is having trouble. I think it's an issue. But a question of priorities there.
Stop being a pessimist.
Let's pivot away from this as well then, and let's go on to our final story, which was about things that I said could make us go boom.
Yes, indeed. Well, there's actually 2 different little stories here which I thought were worth combining. And the first is something which actually maybe did marginally make the Earth go boom, and that is evidence. Well, these are both about asteroids, or in fact meteorites. So just for clarity, an asteroid is a chunk of rock in space. A meteor is a chunk of rock formerly known as an asteroid hurtling through the atmosphere, and a meteorite is a chunk of rock formerly known as a meteorite, formerly known as an asteroid, which has finally reached the Earth. Is that correct? Did I say that right?
Yep.
Yeah, good.
What's a Super Bolide?
Sorry, go away. So this is about, they have oldest records. So there was a story just the other day about the fact they found the oldest crater on Earth, they think, which is dated at 2.2 billion years ago.
It's pretty old.
Pretty old. It's a pretty hefty crater. It's in Australia, near Perth, I believe, and it's about 50 kilometres across. So it's a fairly sizable crater. There's obviously not a lot left of this by this time. The moon is bombarded merrily with craters, and every crater that's ever been there has sat perfectly intact, not weathered away. Nothing's happened. There's been no tectonic
unless another crater erases it.
Well, yes, and it sits as a pristine sort of record of that event. Whereas, of course, on the Earth, they very quickly get but on Earth timescales, quickly get sort of covered up, or the rock will get reformed, etc. And they found this. They found evidence by looking at the magnetic properties of the rocks, which have apparently been marginally changed by as a result of melting and then reset or cooling after the impact. And there's a large region in which there's apparently a small kind of unexplainable raised anomaly in the middle, which they think is kind of effectively, because sometimes it's a bit bizarre, but in really big craters where you totally sort of blast the surface of the planet, you actually get a bump in the middle. So you kind of imagine a crater just being a big sort of bowl-shaped thing, but actually if there's enough melting of the Earth's crust, then the liquid kind of flows back into the middle and you get a kind of raised section.
It's like when you see the slow-motion water drop.
Yeah,
there's always a back in the middle because everything comes back. And
so I think that was how they pointed at it. And the thing that they got particularly interested about is the fact that this would have been a pretty hefty impact, and it's around the same sort of time frame that the Earth ended its kind of snowball Earth history. So Earth at some point would have been basically, I think, almost completely covered in ice, and then for some reason there was a transition at which the atmosphere would have changed. There would have been enough heating, and then through huge amounts, so I suppose effectively global warming, you'd have got feedback processes which you would have melted some of the snow, you get less light reflected, the planet gets warmer, and we end up with a planet we've got now. And they think, okay, the error bars on these measurements are massive, but it's of order, within the same few 100 million year window, which is kind of quite cool. Quite nice.
I like that. Yeah. Were they doing that gravity anomaly thing to try and find?
They said they've been studying the rocks themselves.
Okay.
But equally, I have to confess, I haven't looked a huge amount of this. I just thought it was kind of interesting. And I spent more time actually looking at another story, which is about an even older thing, which I think is kind of actually more exciting. And that's the oldest rocks on Earth. So Earth is 4.5 billion years old-ish, as is the solar system. We've just been talking about an impact from 2 billion years ago. The more intriguing thing is they've found some evidence of rocks on Earth which are, they think, up to about 7 billion years old. Which obviously sounds at first sight ridiculous, but these again have been brought in a meteorite. And in fact, they're not really rocks. They are tiny dust grains within a larger rock. So what they think this is evidence of dust which would have been in our solar system when it was forming. And then the dust, so the dust would have predates the solar system. It was formed, actually intriguingly, it was probably formed maybe in another dying star, so something like Betelgeuse.
So the dust that we're mostly made of condensed out of our own solar nebula, but this is older dust that had already been dust before it arrived and got arrived
in. So most of everything we kind of...
Is it like a fly in the cosmic soup? Is that what you're saying?
Yeah, I suppose so. I think, or a raisin in a kind of crumble. No, that doesn't work. No, that's terrible.
I'm just hungry now.
But effectively, so you had asteroids forming in the early solar system. At the same time our planet was forming. You got chunks of rock forming, and they formed effectively around small dust grains which predated our solar system, which is
kind of epic.
It is very cool.
So I'm guessing you're radio dating. What elements do you use for a 7 billion year?
You look for, and this is where it gets a little, I think I'm intrigued. Mm-hmm. You look at neon 21, which is
but of course,
an isotope of neon.
My personal favorite.
Yeah, which is, well, it should be. It's very good. It is formed from the decay of silicon carbide, which you would find in most rocks. Would have it.
I was going to say telescope mirrors, but yeah, sure.
Probably that rocks too. As it's hit with high energy cosmic rays. So space is filled with cosmic rays coming from all manner of extreme events. If you just go and sit in space, you will slowly get bombarded with these, relatively slowly. Don't panic, astronauts. And actually, in fact, we get slightly protected by the Earth a little bit, obviously. But if you're an asteroid sitting around in space for a long time, you can guess the age of the asteroid by the amount of neon 21, because it tells you how long it's been exposed to cosmic rays. I'm intrigued because to do that, you must have a pretty good handle on the current rate of cosmic rays around the asteroid belt, which we probably have, but also the rate winding back the clock by 7 billion years, which I'm kind of impressed that we could be confident about. To be fair to the paper, they say the rocks are the dust grains are between 4.6 and 7 billion years.
So that's quite nice because it's all
older than Earth, but it's definitely a big error bar.
But getting a handle on on the rate of cosmic rays, I can't see any reason it would have changed that much over 7 billion years.
Well, I don't know whether it would have changed in relation to other galactic activity. So if in the earlier history of the galaxy you had, even if the Earth was nearer to higher energy sources, so if it was near to a cluster which had recently formed, and so you had lots of supernova occurring at some time.
It's quite likely we weren't alone, is that not? The default for most stars is they don't tend to form in isolation. Yeah. Even Betelgeuse, which is shooting off on its own right now, there's evidence if you trace it back, it was part of this association of bright stars. I think it's part of Orion's belt. Three stars that are there, it used to belong to that Pali group, and they're sort of spreading out over time. Betelgeuse has almost been ejected, so there's even a theory it might have merged with another star, and that's what helped give it the kick to shoot it off in the direction it's moving in. But yeah, so we'd have formed in probably a much denser environment than we currently are. The sun sits in a relatively nicely isolated bit of sky, which is possibly not a coincidence. It's maybe handy for life.
It's maybe useful for life. But they think that this sort of points at the idea. Well, one of the things I think kind of hints at, I'm getting really carried away, but they're saying that they think the frequency of these dust grains being old, or they're all within that kind of window, or majority of them are in that window, they think possibly hints at the fact that they think peak star formation for the Milky Way would have been about 7 billion years ago. Now, I have to say, I didn't know that fact until today, so I'm not sure what the error bar is on that, but they're saying that if you wind the clock to about 7 billion years ago, you give a little bit of time for stars to evolve to the sort of Beetlejuice phases, they then start spewing out loads of dust, and you would have a greater density of dust grains in the Milky Way resulting from that burst of star formation. So if you were to find any dust grains in a rock, in a meteorite, in any stellar system now, you would expect to find them to be more likely associated with that period of the galaxy's history, which is kind of quite cool. I mean, there's quite a lot of extrapolation and ifs in that.
Do they use the term archaeoastronomy? Because I've heard it used before to try and figure out, here's that galaxy, and we're trying to work out where the heck that dwarf was that's now getting shredded, or trying to just take a thing that you can see and trying to work out what the heck it was a while back. I kind of like all that stuff. But as you say, it's kind of like archaeology here. You've got to be really careful in context. And
you can build off, kind of say, well, this happened then, which means that happened then, which means that happened then. And if your first one is out by 5%, then your last one is out by a lot.
I guess it's good because this is probably something we've not gone looking for actively in all of our meteorite samples.
No, I don't. Actually, that's true. They said this was they'd revisited. This is I wrote it down. Murchison.
It was one of the famous ones.
Which is the famous one. It's it was a 100-kilogram rock which fell about 50 years ago. So it's relatively recent. So it's quite a pristine.
I believe it's a carbonaceous chondrite, but it's one of your more pristine ones. So it's good in terms of organic-y bits.
I guess maybe that's why it's being studied in this detail. But maybe it's
I say organic like it's moss. No, it's the sort of the pre-organic stuff. But yeah, there's some interesting carbon-based things in there. But yeah,
I think it might be that if this is a more studied one, it's a named thing for stars. Ali knows all about it straight off the bat. I'm not saying that you don't know about all meteorites.
I think the reason I know it is because I think it's one of the more famous of those pristine ones. So if you want to really hold the most unchanged thing in the solar system, you would hold a carbonaceous chondrite, I think. And I'm probably entirely wrong on that if we get a meteorite expert, but I'm pretty sure that's one of the less changed, because you can slice them really carefully and polish them. And you see little granules, little circular features. And so they're pretty much the first things that were congealing, and they've sort of remained as embedded those features and haven't been metamorphosed or whatever. Earth's rocks are changing all the time because gravity keeps squishing them and plate tectonics and everything. And which is why you can't find old rocks, because they've all been changed beyond recognition.
And similarly, you can't find the old dust grains. So there would have been, if a small rock sitting in our early solar system sort of embedded in a few dust grains, the planet would have embedded in huge amounts of
but I'm guessing as soon as you heat it enough, it's gone, vanished, and you'll never see it again. Yeah.
But it's quite cool because, as you say, that sort of thing that we often say to kids of when you're holding a meteorite, you're like, this is the oldest thing you'll ever hold. It's 4.5 billion years old. And I also say, it's a time capsule from the early solar system. It's like, actually, some fraction of that rock could be even older than the solar system. And it's not only a time capsule of the solar system's formation, but of stars which predate our own stars. That's even cooler.
It's kind of fun. Before you even get onto the date thing, I just like holding my own meteorite in my hand and going, that's not from planet Earth. And it's quite a sobering thing to just go, this is cool. And it's so common that I can buy it for a few quid in my rock and gem shop down the hill. Just nice.
You'd have to go and cut it open, look for some dust grains.
Well, like there was us moaning about the last decade and going, it took its toll. And you're holding this thing that's literally counting in billions, and you're like, yeah, it's all good.
Martin is currently looking at his wedding ring.
Oh yeah,
which is made of meteorite.
Does it have dust grains? Quick, look. I think apparently you have to dissolve the pre-existing stuff in acid to get out some of the dust grains. So maybe I'll do that.
I'll ask when I get home tonight, but I might get a no.
But Martin's one, you're iron and nickel, right? So you're not stony, so it's a more changed
very good
thing.
Point.
So just like.
Well, I think that story has nicely blown the dust off our podcasting abilities.
Yay!
So I think we'll leave it there this time and hopefully be back
2030.
A little bit sooner than that. Thank you very much for listening.
Bye.